Hey everybody, welcome back to AV Cyberactive. And in this course of security architecture, we're going to talk specifically in this module about security implications of different architecture models. So as usual, let's go ahead and take a look at what we'll cover in this module. We have architecture and infrastructure concepts, and then we'll cover things like cloud, infrastructure as code, containers, and then we have considerations, things to talk about when we either are designing or assessing these different networks and so forth. Things like availability, resilience, and cost. We'll go ahead and pause here for a moment if you like to understand what's coming, and then when you're ready, let's go ahead and get started. So I guess the big question really is, why is it all important? Well, design decisions can have security and also financial implications. For example, it's much harder to pivot to future. If we make a wrong decision in the beginning and we build an environment on top of that, it becomes harder to pivot down the road if we decide. So doing the due diligence, putting some time and effort and thought into the way you're going to design your network, the parameters, the processes, the technologies, and so forth, all can have a major impact down the road. And as I mentioned, it's costly to shift to newer platforms, and then it builds an environment potentially, again, not always, but potentially to an insecure, inflexible foundation. And then lastly, we have things like vendor lock-in, which may or may not be a big deal depending upon your vendor, how much you like them, how stable and resilient they are. But if you put all your eggs in one basket and that ends up being the wrong basket, again, it's hard to pivot and take decision or new direction. However, if it's designed properly, some of the benefits include flexibility and agility. You build in resiliency, security, and also availability. So all of the things that are a bit of a no-brainer when we are talking about design, but again, if you do not do it properly in the beginning, these things are not guaranteed. Now, when we are building things around the cloud, whether it's on-prem or in the cloud itself, whether we are doing like cloud native or cloud on-prem, whether we are doing full-blown hyperscaler cloud or like an on-prem cloud version, there's a delineation between where responsibilities lie. Cybersecurity responsibilities are typically shared between the provider and the customer to ensure all of the aspects within the security are handled appropriately. And it's pretty crucial that we understand where the delineation lies. So, the matrix or that line in the sand will change depending upon the cloud service model. Whether it's infrastructure as a service or IaaS, platform as a service PaaS, software as a service SaaS, and things like that. Now let's take a look at this. So you can see that we have a little legend on the corner, customer managed and provider managed. So in an IaaS or an infrastructure as a service model, you can see customer managed is on the top section where here are the things in the ping. So identity as in management, user behavior monitoring, data encryption, application security, middleware security, network controls, and the operating system. So pretty much all of the stuff from the operating system up is the responsibility of the customer. The actual provider does physical security, does the networking, virtualization, and basic infrastructure like storage, network, compute, all of those things that you would assume, and that is behind the scenes or behind the curtain. So you don't really have visibility into how those things are accomplished, nor do you care typically. But again, as a security professional, you want to make sure that you vet their practices to make sure they are in line with yours and at least as good as, if not better. And then we talk about platform as a service. It kind of moves up the stack, so the provider will manage a lot of more things of that. They take care of the operating systems, the networking controls, and then the middleware security. So basically, you're looking at application security, encryption, user behavior monitoring, and then IAM or identity and access management. But there are still things that the customer will manage, but it becomes a lot less. So the provider manages the vast majority of that. And then when we go into the things like software as a service, they pretty much they will take care of everything. The customer is only really responsible for user behavior monitoring and then the identity and access management. So the key takeaway here is that if we go up the stack, IaaS, PaaS, and SaaS, the provider manages much more. But even in the SaaS model, there are still some things that are responsibility of the customer, making sure that the user behavior is done correctly and securely. So training is key here. And then also the identity and access management to make sure that you're giving the access only to the people or the folks that need access and not just everybody. Okay, now let's take a look at the various types of clouds. So we have a private cloud. That's basically where you manage and maintain all resources. So in a sense, you manage everything. You become the provider. So it could be a SaaS, IaaS, PaaS environment, and then we shift 180 degrees to the opposite direction. We have private cloud. So in this model, the private cloud provider manages the resources. Everything is hosted. You simply control the data. And then we have a hybrid where it's typically a mix of public and private. Resources are typically created internal, private, and then scaled elastically to the cloud as needed. That's a typical way to do it, and it's not the only way, but that's typically how hybrid cloud would be used. And then we have the community version, which you may or may not see. That's basically where the resources are shared among the several groups, companies, and organizations. It can be public, private, but costs are spread across various members. So again, kind of a co-op arrangement if you would like to go that way. So to make sure that you understand the concepts and various concepts, let's talk about X as a service, right? It's a bit of a buzzword. So you can insert the buzzword as service. It could be anything. So it could be anything that you would typically provide either to yourself or to customers. If you automate that and turn it into a service, then it becomes X as a service. Now it really boils down around virtualization and commoditization of almost every layer of the IT stack. It could be networking, storage, compute, database, etc., etc. But what it really does is provide for a quicker deployment along with increased high availability or HAs to say, and disaster recovery or DR. And as I mentioned, infrastructure as a service, IaaS, allows for distribution and consumption of resources as a service, as the same name implies. Multiple users can utilize the same infrastructure. So if you have multiple customers utilizing the same gear, that's referred to as multi-tenant. Just like an apartment building has multiple people living in that building, they're using that facility, it's a multi-tenant facility. Same concept here when we're talking about the infrastructure as a service. We have a bunch of servers that aren't being used simply by one person or one group. We could have multiple groups, and that could be internal or external to the company. And what that does is it allows for elastic scaling as needs and demands increase or decrease. It's typically priced at a utility model, and what that does is shifts the company's spends from CapEx to OpEx. In other words, instead of having to buy everything upfront, they buy just as much as needed, and then they only pay for what they use. Then they have a recurring month billing after month versus CapEx, where you might buy it once and then you would depreciate the access of the asset over X number of years, typically 5. But if you're doing from an OpEx model, this really is no end to it. You just pay for what you use. Its consumption is based like on the utility would be, and it just gives for the life of the project or the life of that piece of infrastructure. So again, this can also be public or private depending upon how your company structures things. As you can see here, it's made of different things like CPU, storage, interconnect, or networking. All of these things are kind of bundled together and given to the customer. So they don't have to worry about doing any of that stuff. They simply deploy their servers in their infrastructure, whether it's manual or automated. If they need more, they'll scale up again. Could be manual, could be automated. And when they are done using that or don't need that additional resource or resources, they can scale back down, tear those things down back to their bare minimum, so you're only paying for what you need. IaaS also lends itself to automation, so it leverages automation and self-service, which enables a customer to select their own hardware and software configurations and provisions their own infrastructure. So here we have a user as an example. They would log into a self-service portal, and from there they would choose their configuration. All right, so That could typically be a small configuration. As an example, it could be one server with one CPU, a certain amount of RAM, and a certain amount of storage. Or they might need a medium size, could be larger, beefier server with additional CPU, additional RAM, and storage. It could be like a larger server, right? We're kind of doing t-shirt sizes here, so to speak. Small, medium, and large. A large server would have even more compute, even more storage, and RAM, etc., etc. So it allows them to kind of choose between different sizes as they need. And if they need additional resources, they can be scaled up, as I mentioned, and torn back down when they aren't needed. Next, kind of going up the stack a bit, we have platform as a service. So PaaS environment is comprised of computational resources. It could be test and dev environments, and these things can easily be created unconfigured. So the benefits are really, there is really no need to order and acquire hardware and associated infrastructure. Test environments can be quickly created, expanded as needed. We can run tests, we can run reports on those things, and then tear those things back down on demand. And again, multi-tenant where many users can use the same resources. So the benefit really is sped up to the market. There is no need, as I mentioned, to acquire the rack stack, configure hardware, configure network, obtain IP addresses, load balancers, virtual local area networks or VLANs, install software, configure, and so on and so forth, right? There's no need for that. The list continues. So all of these things are taken care of ahead of time or by the provider, allowing the actual customer and the developers to really focus on what they need to do. So as an example, platform as a service or PaaS providers would be AWS Elastic, Beanstalk, Microsoft Azure Application Service, and I'll just kind of go through the rest over here. I'm not going to go through each one individually, but you get the idea. There are a number of different scale kind of hyperscalers, as referred to, organizations out there that provide all of these services to customers. And then they're multi-tenant as well. You can have potentially hundreds of customers on the same hardware, which allows for our economy to scale and allows the customers to pay, as I mentioned, only for what they consume. Scale up as needed, tear back down when they're done. Moving one level further up the stack, we have software as a service. So a SaaS offering or a software as a service is basically an application that's provided on demand. So here, there's no setup, no installation, no configuration required, nothing. Everything is taken care by the SaaS provider. All you need to do is consume that application. So example might be Salesforce, ServiceNow, Office 365, Google Apps, and so forth. Just understand the distinction between these different groups and how they play their role into your overall architecture. Okay, now let's talk about infrastructure as code, or ISA. So this is a methodology to create repeatable processes for deploying infrastructure. What it does, it replaces static scripts, whether it's bash scripts, etc., and then it allows for collaboration and automation with tools like Puppet, Chef, Ansible, Terraform. There's a lot of things out there that can be accomplished, these tasks, but they have the same main goal, which is basically enabling speed of delivery and reducing errors by taking the manual part out of the process. So it reduces shadow IT and it makes processes more secure. And as I mentioned, reduces the risk of human error. And one of the things kind of associated with infrastructure as code is referred to as CI/CD pipeline, continuous integration, continuous deployment. And there are a lot of tools out there for CI/CD pipelines where you can build in. You may have heard about some of these tools like GitHub or GitLab. There is Jenkins, and there's a lot of different tools out there that they can do these things, typical type of activities. GitHub is very, very popular one, perhaps probably one of the most popular. So I'll just give you a high-level example, but by doing this, it allows you to have version control and allows multiple developers to work on the code, check the code out, make things and changes on the code, merge it back to the main code, and so forth. It allows us to speed up the delivery and make incremental or iterative changes, ultimately multiple times a day in a high-functioning environment. So let's say, for instance, we have the main branch, and what a developer would do is check out the piece of the code from the code repository. So when you check out that branch, you basically would then go to, let's say in this example, a redeployment branch. So from there, the developer can make changes, do a pull request to make sure they have the latest, greatest version of the code, and then they would do some type of automated testing. And in this case, GitHub Actions is the part of that testing apparatus. So the code changes that they would introduce would get tested and it would be completely automated. Or it may have some manual steps in there as well. But it's tested to make sure everything works and that doesn't break anything. And from there, these fixes are committed, and then we have to make the decision, did it pass, yes or no? If it did, great, goes up to the next step. If it not, then it's sent back to the beginning and the developers are notified to fix whatever the issue was, and then the process repeats over and over again. But if it passes, then we approve the pull request, and then it gets merged back to the main branch and deployed back into the production. Okay, so let's talk about serverless computing. So this is a bit of a misnomer, but I'll make the analogy and that hopefully makes a little bit more sense. So serverless computing can be thought of like enjoying a meal cooked by someone else in their kitchen, but instead of cooking at home, you decide you want to order a pizza as an example. Well then, you order the pizzas, you don't have to worry about cooking or managing the oven, the electricity, the gas, or the kitchen appliances. So you enjoy the party with your guests while someone else takes care of making and delivering the pizzas. So in a similar way, serverless computing allows developers to build and run applications without worrying about the underlying infrastructure, much like you didn't have to worry about cooking for the party. So when I say serverless doesn't necessarily means that there is no server involved. So someone else is managing them, obviously. The user or the developer really only cares about developing their application. So what this does, it enables the speed of deployment, but it can also introduce potential security challenges as visibility into that environment is limited. That's where due diligence needs to come into play to make sure that you do an audit to make sure that person, that facility, or that company to say their security posture and their policies are in alignment with your own. Another concept that you should be aware of, especially when you're talking about DevOps or infrastructure as a code, is the concept of microservices. So, a microservice is an application that is really structured as a collection of loosely coupled, independently deployable services. So what does that really mean? Well, it basically means that we are talking about an application that used to be, or I'm doing an air quotes here, monolithic application. It might be a black box, in other words, where information goes in and then the information comes out. We're not really sure what happened behind the scenes. Well, in this instance, we're talking about application and we are breaking it up into smaller, more manageable pieces for all intents and purposes are more or less standalone. So in other words, each can be deployed independently, patched, updated, and also scaled. If we need more compute, we then need more networking bandwidth. We need more load balancing capability. We now have the ability to scale those individual microservices up dependent for each other. So it allows for decentralization and again, speed of deployment because now we can have multiple people working on together or individual components versus having developers working on an entire application at once. So as an example, here is a monolithic architecture we talked about that just a moment ago. So here you basically would have the user interface, business logic or data interface, and the database things, all the things that make up the application and are all one big gigantic application. Well, in a microservices architecture, we'll break up all the things. We still have user interface, but behind the curtain, we have a number of microservices. And you'll notice each microservice for the most part has their own database. So they have their own collection of code, their own collection of base, and they have been upgraded, patched, and so forth independently of each other. As an example of a microservice architecture, when we are talking about a specific application, well, we have a mobile application that connects to an API gateway via REST API, right? It's the method of how they actually connect and call API gateway. And then we have a web browser that would access the same backend. But now they're coming into the web application through a web request. So behind the scenes, however, they are issuing REST API calls to different microservices, the account service, the inventory service, the shipping service. All of these things operate independently of each other with their own runner services and so forth. And then they connect to their own databases that track their code changes and track all the code, so that way, as an example, if you found a bug in the inventory service or you wanted to add an additional feature, well, you wouldn't have to actually address the entire code base. You wouldn't have to update the account service or shipping service or all the other things that might make up that application. You could just patch the inventory services, push that patch out, and the application will be upgraded. So, some microservices key points. Here the applications are broken apart by function. All services are created individually, deployed separately from each other. Each component is loosely coupled. So as I mentioned, different groups can develop different functions, as each service can be changed and upgraded without affecting others. They could even use different code bases or even programming languages. Whatever tool works best for that individual team. And then also it can be deployed via containers. So Kubernetes, Dockers are typically used, and each microservice is packaging as container image. And again, when we are doing all of these things, we have the security in the mix as well. They may use to contain code analysis, and they'll do the code analysis as it goes through the CI/CD pipeline to make sure it's pulling from the proper repositories to make sure there's no vulnerabilities being injected. It's not pulling things from places unknown out on the internet right away. They are all approved repositories and so forth. All of these things can be automated and built into CI/CD pipelines, so these microservices are updated. All of these things kind of kick off and take place. And we also have the ability to scale quickly. So scaling is done as a part of changing numbers in the container instances. And then we have the pipelines triggered, so that as soon as the new feature or a code is pushed, it automatically kicks off into the pipeline, builds out a test case, runs it through various environments, and once all the smoke tests are complete, and we understand that the code is functional, so it doesn't break anything. And now it can be deployed very programmatically out into the production. Okay, next, so let's talk about software-defined networking. So software-defined networking, otherwise known as SDN, is an approach to networking that implies software-based controllers or application programming interfaces, or APIs, to basically decouple the management plane from data plane. So in other words, the intelligence is not necessarily built into the machine or to the router versus having the functionality hardwired or hard-coded into the appliance. Now this places the intelligence higher up the stack, and it automates or allows the automating of most functions. And it also allows for a holistic view of the network and programmatic tuning based on activity, on workloads, and so forth. And it adds more intelligence. It allows an operator to see entire network at a glance instead of looking at each individual machine. And you can also control all of the routers and switches in the environment from a single pane of glass. So in the essence, the routers and switches become dumb devices with intelligence handled by a centralized controller suite versus each individual device. As an example, in a traditional sense, the operator or an administrator have to go around each individual router and switch, and they could access that remotely over the network. But they would have to log into each individual switch one by one throughout the network, for the routers and the switches didn't necessarily have visibility to each other. They were all more or less standalone devices on the network. Using a software-defined network strategy, we can push out patches, updates, and so forth out on the entire environment at once, or programmatically maybe doing a few at a time, but it allows us to dramatically speed up the management of the network, and it allows the individual devices to communicate with each other efficiently, so they have a better view of network and how traffic is proceeding. Next, let's talk about on-prem versus off-prem. So on-prem, as you might have guessed, your own infrastructure, you have more control on customization and non-standard builds. So I'm talking about servers, desktops, storage, whatever the infrastructure might be. When it's on-prem, you own it. You can control how it's built and how it's managed. You can also have more direct control over policies, management, administration, and so forth. The downside is you have to manage the entire life cycle of those individual devices, and it's also a capital expenditure called capex typically. When you pay for the entire cost of the device upfront and then you depreciate it, it depreciates over time. And when we are talking about off-prem, and when I say off-prem, I'm referring to hosted or cloud environments. So in off-prem environments, you don't own the equipment. It's managed by the provider. So they take care of the patching cycle, all that good stuff. Now you have less control over customization, less control over policies and overall administration. So that could be a plus or a minus depending upon how you look at it. Also, no life cycle or maintenance activities. So you could just consume the infrastructure. You don't have to worry about projecting life cycle activities and all of that stuff. And then patching and security, as I mentioned, is managed by the provider themselves. And then we have the opposite of CapEx, which is OPEX, operational expense. So if you don't pay for the entire thing upfront, you only pay for how much you use. You pay for it month over month. Now the downside is that it will last in perpetuity or as long as you're actually using the infrastructure. Whereas when it is a capital expense, after 5 years, it's fully depreciated. Now again, most organizations will not keep the infrastructure longer than 5 years anyway. So you're going to go out and basically buy a new device as soon as you're done paying for it. But at least you don't have to pay for it upfront. So with OPEX, you typically just pay a monthly fee and that just continues for as long as the project or whatever isn't actually in operation. Okay, next, let's talk about virtualization. We talked about it briefly before, just understanding the virtualization infrastructure. So we can now talk about workstation. It could be servers, it could be storage, networking. So it's not just a server or a desktop. You can pretty much virtualize any piece in the IT stack. And just for your information, in case you're not familiar with virtualization, there are a few major players in that space. So we have VMware, we have got the Microsoft Hyper-V, and then another one is called KVM, and then Oracle. They all have robust virtualization products. VMware is one of the biggest players in that space, but by no means they are the only player. And having said that, all the virtualization technology operate in more or less the same fashion. Although they are different in management suites, but they are different ways of controlling and operating and administrating these things. But the basic concepts are the same. So what it does, it takes the capability and the personality of physical device and it converts it into a virtual representation. So instead of having a single server, you can now have multiple servers existing on top of a single server or a physical server, and it can perform the same functions as its physical counterpart. It lowers infrastructure costs, but it will raise typically your licensing costs because you have a hypervisor license. You may have to pay for a number of CPUs in your host, right? There are different things that will be stacked on, but in the grand scheme of things, it's typically cheaper and it allows you to migrate and move things as little more easily. So virtualize as an example here. Here we have a traditional server, right? And you see we have the server, which is the bare metal piece there. There's an operating system that's applied on top of that, and then on top of the operating system we have the load of our applications within a virtualized environment. And in this instance we have VMware, we have our bare metal server, we have VMware on top of that, and that's our virtualization platform. Now we can install multiple operating systems and multiple tests of application. Each one of the block here is actually a separate virtual server sitting on top of the physical server. So in other words, you could have a physical server that might host 30 or 40 virtual servers. All act completely identical to the physical counterparts. They have everything that a physical server would have: its own IP address, its own operating system. You could even have several that are Windows You could have several that have Linux, Mac, and others. It doesn't really matter. So they function for all intents and purposes the same as the physical server. Again, a VMware example, we have an ESX or ESXi host. And then on top of that, we have 4 different servers here, which you can see. We can dive up the amount of process or the amount of RAM and so forth that these virtual servers are getting based upon the needs of the server. So in this case, we have 4 different servers and one has 4 CPUs, one has 1, one has 2, and so forth. Now, they could have been different operating systems, again, all acting as if they were true physical servers. But they have been virtualized sitting on top of that physical server, and the physical server has basically a pool of CPU, a pool of memory, a pool of storage, and networking and interconnectivity. So those things are then divided up to the guest or the servers, the virtual servers that sit on the host machine. So that's otherwise known as multi-tenant environment with multiple virtual machines or guests on one hypervisor or host. Now we have type 1, which is basically the host runs on a bare metal server and the guest runs on the host. Now VMware vSphere as an example, individual guests can be Windows or Linux or any other flavor of operating system, and these are more suited to enterprise environments, right? So management tools for optimizing or advanced virtualization management and automation are built into the operating system. So there is no other operating system sitting on top of that bare metal. The VMware ESX ecosystem is the operating system running on them. Also, we have type 2 that basically has a host that runs on top of the OS and guests run inside the host. So VMware Workstation or VirtualBox, newer version of Windows, have virtualization technology built in as well. We have a server that actually is running Windows or Linux, and then on top of that we have VMware. Now VMware run at a third layer above the hardware, and this is more suited for desktop environment for development, testing, desktop virtualization, and so forth. They are usually slower and less performant. They have less management functions and automation functions than type 1 hypervisor. And then we have the container based. In this is the operating system virtualization, very lightweight. Containers can start up in milliseconds and they share the OS kernel. Also, they typically contain the application in binaries but not the operating system. You may have heard about the Kubernetes and Docker, which are both containerization platforms that allow for us to deploy containers very quickly. And you will see this in microservices architecture where you would want to be able to spin up containers very quickly, and these things lend themselves to like web applications or things that have very high demand or potentially high demand. Like you might run a commercial during the Super Bowl as an example, and then all of a sudden you might have been going to 3,000 visitors a month to 20,000 visitors a day. So you don't have to pay for 20,000 servers in the entire year if you only need that for a day, for an example. So by having things in a containerized environment, you can very likely scale up the demand, meet the demand, and then when the day is over or the week is over, scale back down. So that way you're only using and only paying for what you need. Okay, so now when we talk about Internet of Things or IoT, we need to remember one important thing. Everything conducted in the internet is a potential target. Every new device, from obvious entry points like computers and routers down to smaller devices such like wearables, creates an opportunity for hackers. Our networks are full of different devices, and each entry point are increasing every single day, so IoT plays a major role in this growth. So why exactly do we mean by IoT or smart devices? These include things like wearable technology, smart home devices, connected sensors, and automation systems. These devices are designed to always stay connected, and they continuously share information such as location data, daily habits, and other telemetry. While this constant connectivity can be useful, it also means that attackers have more ways to intercept data and break into a system. If organizations and individuals don't fully understand how these devices work or fail to secure them properly, the risk of a breach becomes much greater. Take home automation systems for an example. They may handle a large amount of sensitive personal information, from financial details to private information. If these systems are not secured, Attackers could gain not only just the data but also users' wider digital life. This risk doesn't only apply to individual homes, it also affects small businesses, large enterprises, and entire organizations. The more IoT devices are deployed, the more common these risks become. There's also another factor to take into consideration: the role of social engineering. Hackers can exploit the personal information gathered from IoT devices to learn more from an individual. The more you know, the easier it becomes to trick them, manipulate, or deceive their target into giving up access or information. IoT devices come in many forms: sensors, wearable tech, smart appliances, and building automation systems, to name a few. These tools make life more convenient, efficient, in real time, but they also expand the attack surface of any organization that uses them. And why is this expansion so dangerous? The main reason is that the most IoT devices share common weaknesses. Typically, IoT devices are low powered, meaning that they lack the processing ability to support stronger encryption or advanced security features, or they are shipped with default username and passwords that many users never bother to change. These weak and defaults are limited security protections make IoT devices prime target for attackers. That's why securing them is so important. Now, good practices include changing default settings and passwords immediately after setup, routinely auditing your network to identify which IoT devices are connected, and understanding what data each device collects and transmits. Okay, so let's talk about something referred to as SCADA system, or SCADA. We're basically talking about supervisory, control, and data acquisition systems. You may not be familiar with this term yet, but it's very important to understand what it is and the implications of these systems, and if they're not maintained properly. They can have a major impact because these systems usually are referred to centralized platforms that monitor and control entire sites and complexes of systems that is spread across large area. So, what does that really mean? Well, you see here I have a small diagram. What we are talking about are systems that control critical infrastructure like electrical grid, nuclear facilities, or power plants. Things that are extremely important. Again, this is just a simple diagram and we'll dig deeper in just a moment, but let's first cover some key terminology within the SCADA system environment. So we have something called an RTU, or remote terminal unit. This connects a sensor, converting the sensor information, whether it is from a pipe of a piece of an equipment within a larger system, into digital data. These sensors monitor factors like temperature, pressure, voltage, electricity levels, and triggers alerts depending on what's happening. Next is PLC, or Programmable Logic Controller. This is similar to the RTU, but PLCs are often more modern, versatile, and cost-effective. Although they serve a similar function, but both RTU and PLCs report into a Master Terminal Unit, or MTU. The Human-Machine Interface, or HMI, then presents the data collected from the RTU and PLCs to a human operator. The operator then acts on the data, for example, adjusting waves or ensuring conditions remaining within the acceptable ranges, essentially responding to triggers and alerts. The MTU, or Master Terminal Unit, sends information to instructions to the RTU and PLC, receives data back from them, and aggregates all the information. So yes, there's a lot of acronym here, but the key point is SCADA is an integrated system made up of sensors, controllers, and interface. Now picture this. In a SCADA environment, you might have master control room filled with screens showing data from many different systems. This could be at a nuclear power plant, a water treatment facility, or an electrical grid, or even in a sewage system. PLCs and RTUs are spread across entire infrastructure, reporting back to MTU. An operator sits at the control center, monitoring, managing, and maintaining all of it. Looking at this in more detail, SCADA systems have RTU placed along with the network. Traditionally, these networks are closed off, not connected to the internet, often air-gapped. But over time, SCADA has evolved from being isolated, self-contained systems into distributed networking systems, and in some cases, even internet-connected systems. This creates new risks. If a SCADA network is connected to the internet or has some access point, legitimate or rogue, a remote attacker could gain access. That's why it's critical to secure these networks as much as possible. One option is to implement monitoring with a network intrusion detection system, NIDS. Since we may not always be able to install host-based intrusion detection on every device, network-level monitoring becomes especially valuable. Paired with firewalls, this can help detect intrusions even if the attacker connects from an internal network. Now let's discuss a few SCADA security concerns. Originally, SCADA systems were monolithic, isolated, and not designed for connectivity. They operated as closed air-gapped networks, but over time they evolved first into distributed systems, then network systems, and now into IoT-enabled platforms with potential access from virtually anywhere. This shift brings new risks: unauthorized access, malware, hacking, and even theft or destruction of data. This is serious concern because cyber attack on SCADA systems can degrade or even destroy critical infrastructure. Let me give you two examples. The first successful known cyber attack on critical infrastructure occurred more than 20 years ago in Queensland, Australia. A disgruntled employee with the knowledge of ICS industry control system and SCADA exploited that knowledge, using special equipment to release 265,000 gallons of raw sewage into local parks and rivers. Needless to say, it was a pretty disastrous situation. The second example is one you may have already heard of: Stuxnet. In 2010, Stuxnet malware has been deployed as a digital weapon against Iran's nuclear facilities. Specifically, it targeted industrial control systems and PLCs that managed centrifuges at the Natanz plant. Unlike most malwares, Stuxnet wasn't designed for broad attacks. It had a highly specific target. Siemens Step 7 software. Initially introduced via infected USBs, Stuxnet infiltrated the air-gapped network. Once inside, it searched for a specific PLC configuration used into centrifuges. When it found them, it manipulated their operation, speeding centrifuges up, slowing them down, and causing physical damage. Now let's go ahead and shift gears a bit and talk about embedded systems. An embedded system is a microprocessor-based computer hardware system with software that is designed to perform a very specific or dedicated function. They can act either independently or as a part of a larger system, but at their core, it's an integrated circuit designed to carry out computations for real-time operations and real-time operating systems. You might ask yourself, what's the difference between an embedded system and general computer? They sound very similar. The key difference is that the embedded system is designed for a very specific purpose with low latency, and it does that one thing extremely well. A general computer, on the other hand, can handle many different tasks and does a lot of things fairly well. But embedded systems are built to do one thing very precisely, very quickly, and often in real time. Embedded systems have countless applications across many industries, from household appliances, medical devices, industrial machines, networking equipment, and more. However, there are real security concerns when it comes to embedded systems. For instance, they often have limited resources because of their constrained computing power. Traditional security measures can be difficult to implement. They simply don't have enough processing capability, memory, or storage to handle resource-intensive tasks like encryption. They also have long life cycle. Many embedded systems or devices remain for use for years, sometimes even decades, which creates challenges while updating and patching them. Another concern is physical security. Many embedded systems are deployed in locations where they can physically be accessed, making them vulnerable to tampering. If tampered with, and especially if conducted to an internal systems or network, they can become an easy entry point for attackers. You also have to consider connectivity. As more embedded systems become interconnected, such as things like Internet of Things, they have faced increased exposure to network-based attacks. With their limited resources and weaker defenses, including encryption that may be absent or insufficient, the risks grow significantly. Then there is supply chain issues. Component and software used in embedded systems often come with a wide variety of resources, which introduces potential vulnerabilities if those sources aren't thoroughly vetted. As we discussed in another module, ensuring that the supply chain and third-party vendors follow strong security practices is really critical. Lastly, we have legacy systems. Older embedded systems, which are not designed with modern security threats in mind, are particularly vulnerable. This ties directly back to the issues of limited resources and long life cycles. Many of these systems remain in operation for decades with little to no physical protection. If they are network connected, wired, or wireless, they can easily introduce vulnerabilities into your environment. So, when we're talking about embedded systems and IoT devices, keep these challenges in mind. Security should always be your top priority while evaluating, vetting, and auditing your environments. So now a few examples of embedded systems or embedded systems platforms include Raspberry Pi, which you may or may not have heard of, but they are really popular. Raspberry Pi is actually a fully functional microcomputer, not necessarily as an embedded system of its own, but it can serve as a platform or foundation for an embedded system. Keep in mind that a Raspberry Pi, for the most part, is fully functional computer. It has a CPU, Wi-Fi, Bluetooth, USB connectivity, and even video output depending on the application. Since we are talking about that, then we have Arduino board. Unlike a Raspberry Pi, an Arduino board is a single board microcontroller. It is not as featured or functional as Raspberry Pi and is designed with a specific purpose in mind. Another example is a fully programmable gate arrays or FPGAs. These are integrated circuits that can be configured and programmed after manufacturing, making them very flexible for specialized tasks. Now, all of these platforms can make use of what is referred to RTOS or real-time operating systems. When we're talking about embedded systems, a real-time operating system is designed to process data with minimal delay or latency. It's really very fast, very streamlined, and built to do only one thing that is extremely well. Unlike a general-purpose operating system which tries to maximize the amount of work it can perform, an RTOS is more concerned with deterministic processing of data. So, what does deterministic mean? It means that we know exactly how long a specific action will take, no matter how many times it is repeated. For example, when it processes something once, 100 times, 1,000 times, or 1,000,000 times per day, it will take the same amount of time each and every time. Contrast that with a regular computer, which is often multitasking, running a malware scan, loading a video, juggling countless tasks, making it hard to predict how long one specific operation will take. But in real-time operating systems don't have that issue. They do one specific task very, very well in a predictable and deterministic fashion. Because of that, RTOS platforms are usually dedicated to a narrow set of functions. As I mentioned earlier, these include embedded systems, Internet of Things devices, and SCADA systems, specifically PLCs, that we have discussed before. RTOS platforms are naturally responsive, while containers and virtualization provide ease of deployment and recovery. However, we also need to think about their limitations. We have discussed it earlier that patch availability and patching ability are often major challenges. Low-power devices, like many of the IoT systems, are convenient and make our lives easier, but their limited processing power makes them vulnerable. They can't effectively defend against brute force attacks, and their encryption is often very weak, sometimes no encryption at all. These are all serious security concerns. As you continue to work with IT and security, make sure that you develop the habit of thinking critically about these issues and then evaluating systems, vetting the vendors, or assessing infrastructure on your own environment. Always consider the risks from every angle. Alright, that wraps up this section. So this is all that we have covered today. We covered a lot of important information around embedded systems and related platforms. Stick around, because up next we'll be talking about security principles to secure enterprise infrastructure. See you in the next module. Bye now.